So today we will spend some time describing the angles in the axis, which we will then later use in a derivation of, for instance, the stability. So how do we describe the stability and control? Well, I brought a little airplane here to demonstrate the different angles. We also got a slide on it. Let's first look at what we call the body axis, because there is a reference system attached to the body of the aircraft. So we have a number of axes there. We have the forward direction we call the x-axis. The first x is the one that points forward, the most important direction for flight, as you can imagine. So that forward direction is the x. And as the y direction, we choose the wing, and it has to be the wing on the right side. We will later see why that's a convenient wing to take as a positive direction for the y coordinate. But for now, this means, and that's not very convenient, that if we use the right-hand rule to turn from x to y, that it makes our z-axis point downwards. But that's our reference system as we use it. So with the body axis, we have the x-axis to the front, y-axis to the starboard side, and the z-axis pointing down. We also have, we use this axis to describe the rotations, and the rotations around the x-axis we call roll. So that's the roll angle, or bank as it is also called, to bank the aircraft. So that's the rotation around the x-axis, roll or bank. I'll usually call it the bank angle or roll angle, it varies. So the rotation around the y-axis is this rotation, nose up, nose down. It's what we call the pitch behavior. The pitch angle is the angle with which we rotate around the y-axis. And the rotation around the z-axis is what we call yaw, this yawing of the aircraft. Well, if we look at the symbols that we use for these movements, then here we see the rudder causing the yaw angle, psi. And you also see the sign here. So if it's extended to the starboard side, it has a negative sign, but it results in a positive yawing angle psi. And that's sort of standard for the sign convention of these control surfaces. A negative extension results in a positive angle response. So the yawing angle is, we use the symbol psi for it, controlled with the rudder, which we call delta R. The roll angle, therefore we use the character phi, roll angle phi or bank angle phi. And here we also see that the minus sign of the deflection for aileron left and right, which have an opposite sign convention, corresponds to a positive bank angle phi. And the elevator, pitch angle, theta, again here a negative extension of the elevator, minus delta E, results in a positive pitch angle theta. Well, I used so far the body axis, and they are attached to the body of the aircraft. For stability, we often want to look at a stable situation, equilibrium as a situation, as our starting point, and therefore often the speed factor is used as the x-axis. So the aircraft is normally flying under an angle of attack, and we have the speed factor pointing in another direction than the body axis. And this means we can also use that as an x-axis. And this is more convenient if we talk about stability derivations, because that is our equilibrium, our neutral position. And if we look at the results for our equation, here we see the three different reference systems that we have. We see the body axis indicated by the blue arrow, the aircraft. We see the horizon, and that's our reference for the Earth. And we see the airspeed indicated in yellow. And this means that the angles between them also have different meanings. So the pitch angle, the angle of the body axis with the horizon, theta, is the angle between the green horizon and the blue aircraft axis here, indicated in magenta. And it is, as you can see in this figure, actually the sum of the climb angle, the angle of the speed with the horizon, and the angle with which we climb, and the angle of attack. And the angle of attack is, remember, is the angle between the airspeed and the axis of the aircraft. So from this picture, we can see one of the first equations. Theta is alpha plus gamma. The pitch angle is the angle of attack plus the climb angle. Well, we have a similar situation if we look at the lateral, so the top view of the aircraft. Here again, there can be a difference between the direction in which the x-axis is pointing and the direction that we're flying. And this angle between those two is what is called the side-slip angle. Side-slip angle beta is the angle with which the aircraft slips, and as you can imagine, this results in a lot of drag. So normally you would like to avoid this. During en route, during cruise flight, the side-slip angle will be as small as we can get it. But when doing a crosswind landing, for instance, to avoid having a bank angle while landing, we might introduce a side-slip angle to still be able to have a speed in the same direction as the runway. So the side-slip angle is the angle between the airspeed factor and the aircraft body axis, looking at the top view. And of course here we also have an inertial reference. In this case it's the true north. And this means that if we look at our course, this is the angle between the speed and the north direction. But if we look at our heading, it's the angle between the body axis and the north. And if there's a side slip, then it's different. And then you can see from this figure that the heading is basically the sum of the side slip plus the course, because we have defined the side slip in such a way that when the air is coming from the right starboard side from the aircraft perspective, then we have a positive side slip angle beta. If we look further at the axis, we can also define the symbols for the moments around these axes. These angles that we just discussed are caused by moments, and therefore we use the characters L, M, and N. L for the angle around the x-axis, so L for the rolling moment, not the angle but the moment. M, the moment around the y-axis, and N, the moment around the z-axis, the downward pointing z-axis. So the direction is positive if we turn to the right. Of course, the L was already in use for the lift force, and therefore we write it as a sort of curly L, trick that we also saw with the gas constant. We write a curly L and a curly M and a curly N to indicate those moments. But they are normally not confusing, because the rolling moment has to do with the asymmetrical movement of an aircraft, and it's a completely different domain than symmetrical movements where you work with the lift force. So that's really two different worlds from looking at stability and control, and therefore it's not as confusing as you might think. In our lecture, we'll only look at one of these moments, and that is the pitching moment, so a symmetrical moment, and that's the for which we use the character M. Pitching moment M, and this is the first moment, the easiest moment to look at. Might historically be the reason that is called M as well, and then later L and N were added with the two X's. And there it's important to remember the sign. And this means that if the pitching moment M is positive, if you use your right-hand rule, this means the nose will go up. And that's of course convenient that we have a positive pitching moment with the nose up. And this is the reason that the y-axis of the body axis is extending to the starboard side. That is to have this convenient sign convention that pitching moments up correspond to a higher altitude as a result of a nose up. So that's what we will mainly look at today. But you will see that a lot of times we do not actually discuss the actual forces, but we only work with the coefficients. And why this is best explained using the lift formula that I have here. We see here the lift force. You've seen this before in the forces, the lecture on forces. Lift is the lift coefficient, CL, times half rho v squared, the dynamic pressure, times the surface area of the wing. Well, In stability calculations, we often use the lift coefficient CL as if it is the force. And why is this? Well, let's think of what this actually means. If I would like to design an aircraft and I need to select a certain airfoil for my wing, then if I asked my aerodynamicist design me which airfoil should I take, then if I would be talking about the lift force, he would ask me, so what is the speed that the aircraft will fly at, or the altitude? And I will say, well, I want all kinds of speeds and all kinds of altitudes. And so what's the surface of the wing is going to be? I say, well, it depends on the properties of the airfoil. Well, the aerodynamicist would then say, well, I can't help you then. I cannot tell you what the lift force is going to be because I need all those figures. If, however, I would ask him what the lift coefficient of an airfoil is, then, as you can see from the equation, he doesn't have to know the speed or surface or the altitude, which is in the air density, because the lift coefficient is independent, is the same for all these values for density, speed, and wing surface. It only depends on the angle of attack, a bit on the properties of the flow, indicated by perhaps a bit of Mach number if you fly really fast, or the viscosity of the air. But in subsonic regions, it's mainly the shape of the airfoil and the angle of attack. So it really describes the flow, the aerodynamic flow and aerodynamic shape of the aircraft. And therefore, this is a figure we can use because in the wind tunnel we can measure these, and we can give a little graph, which will then show the way the lift coefficient varies, and you see it here, varies with the angle of attack. And then I can do the calculations, what I need at certain altitudes or speeds to find out what the wing surface needs to be. So we often use these coefficients, which you see here on the left side. You see here the coefficients which we normally use as if they are the forces. But there are some things to pay attention to. That is that the aerodynamicists that calculated those lift coefficients for us, of course, didn't know what the surface area was of the complete aircraft that we were going to use. So if I get a lift coefficient for the tail surface, then to get the actual force, I will have to use the tail surface area and the other way around. So from the lift force of the tail surface area to get to the coefficient, I have to divide by the tail surface area, indicated here by SH. So we always have to think what type of coefficients we are talking about. If there are coefficients for the complete aircraft, then the wing area of the complete aircraft is used as a reference. However, if we look at properties from an airfoil, from an independent wing surface, then in general the area of that surface will be used. So this is something we have to be careful to, what's surface to use. But if we pay attention, then we can use these coefficients as if they were the forces. But for moments, we basically do the same. We divide a moment by half rho v squared s. But as a moment has the unit Newton meters, that doesn't make it dimensionless. And in fact, if you look at the chord, this is, this scales with the arm of the aerodynamic forces. So if we divide by the chord, we take out the scaling effect, and we have made the coefficient completely dimensionless, as we call it, which means unitless. The half rho v squared s times the chord, the unit of this complete multiplication is Newton meter. So by dividing the moment by Newton meter, we have made a unitless, which we call dimensionless coefficient. So bottom line is that CL, CLH, and CM are for us basically forces and moments without dimensions and also without the influence of altitude and speed or surface area. So they are valid for the shape of the airfoil and the current angle of attack. And that's where we'll use them, because that's very convenient in the derivation we will do in the next lecture.